These are the solutions to practice quiz 6. Chromium has an anomalous configuration of argon 4s1, 3d5. How many total unpaired electrons does this atom contain? We did this problem in lecture. So just 1 in the 4s, all 5 unpaired in the 3d. So that gives us a total of 6 unpaired. Number two here, a metal may release, which statement is true about the photoelectric effect? A metal may release photons when it is irradiated with light of a high enough intensity, low enough wavelength, low enough I was seeing what the difference was. I should bold these. Release photons or electrons. So the key of the photoelectric effect is that metals can release electrons, not photons, and it's when the metal is shined with light of a high enough energy or a low enough wavelength. Because as we go to a lower wavelength, we go to a greater energy. So C is looking correct. We don't need the light to be intense enough, because if we have light that's of too high of a wavelength, not a high enough energy, then none of those photons will cause electrons to be ejected from the metal. And then the metal may release electrons when of high enough wavelength. It doesn't want it, you don't want the wavelength to be high, you want it to be low, so it's high energy. So the idea is a metal has a certain amount of energy it takes to remove an electron, and as long as the photon carries that energy, think of the energy per atom of the metal, as long as the energy per photon of the light is high enough, then it can cause electrons to be ejected. It gave us this idea that you can think of a single photon of light interacting with a single atom, and then thinking about the energy of that photon coming off the equation E is equal to h nu, or hc over lambda. So higher frequency, higher energy for a photon, but then lower wavelength, higher energy. Moving on to 3. What is the de Broglie wavelength of an electron moving with a velocity of 1.0 times 10 to the minus 3 times the speed of light? And we want this wavelength in nanometers. Well, our equation for the wavelength of matter, and I like to put the symbol here, you may not see this on the equation sheet, but I'm looking for the particle velocity, and then I'm looking for the wavelength, and it relates to h and m. So this is the wavelength of matter. So I plug in Planck's constant. It's usually useful to know that our joules times seconds is really kilograms meters squared per second squared times seconds, because this unit here is 1 joule. So that's joules times seconds is kilogram meters squared per second squared times seconds. And then divide by the mass of the particle, the electron mass. Now, this particular test was expecting that the electron mass would be on an equation sheet. I'm not entirely sure it's on our equation sheet. So make sure that you see here, we'd have a given mass of the electron, and it's 9.109 times 10 to the minus 31 kilograms. We'd give that to you either on the equation sheet, and if it's not there, we'd put it in the problem somewhere. And so that's our mass of the electron, a single electron mass. And then the velocity is this 1.0 times 10 to the minus 3 times the speed of light. So 1.0 times 10 to the minus 3 times 2.9979 times 10 to the 8 meters per second. So our kilogram cancels, and we want the mass to be in kilograms to cancel into the units from the joule. We want one of the meters to cancel, our seconds are all canceling, and so we're getting out of this equation here the wavelength of matter in meters. And so let's work this out. So 6.626 6.626 times 10 to the minus 34, divide by 9.109 e to the minus 31, and then divide that also by 1.0 times 10 to the minus 3 times 2.9979 e to the 8. So I get 2.43 times 10 to the minus 9 meters. And then 1 meter has 10 to the plus 9 nanometers. So I'm multiplying that by 10 to the 9. Just a little bit more clearly. And so that should equal, I think it should be 2.43, but let me do the math just in case. Yep, 2.43 rounded to placeholders because of this here. So 2 sig figs, 2.4 times 10 to the 9, 10 to the minus 9 meters, or 2.4 nanometers. And so the electron has a wavelength that's on the order of the size of the atom. So that's why the wave nature of the electron is important and relevant to discuss. Not on this activity, at least not yet. The uncertainty principle then says the electron is a wave that we also don't know where exactly it is at any given moment when we know its velocity. So it gets us into probability distributions or the idea of orbitals. Okay, so which of these configurations is that for sulfur? So I can think from scratch, sulfur should just be a 1s2, 2s2, 2p6, 3s2, 3p4. Sulfur is element number 16 on the periodic table, so you should have 16 electrons. So there's 10, that's neon. So that's 10 of our electrons, and then the remaining 6, 3s2, 3p4. So looks like E. Which transition of the H atom below would cause the emission of would allow for the emission of a photon of the greatest wavelength? And so emission's going to occur from high N initial to low N final. So initially in some high state and then transition to some lower state. And then the greatest wavelength corresponds to the lowest energy change for the atom. And so when I'm looking at the emission, I don't get emission for A because that's low to high. I don't get emission for B, that's low to high. I certainly don't get emission for 1 to infinity. That's the idea of ionization of a ground state H atom to H plus an electron. You may wonder, well, what is this? That's really just the idea that that's the electron removed from the atom. So I get emission in D and E, and the 2 to 1 difference is humongous. Then the 3 to 2 is smaller, than the 3 to 2 even smaller. So if this is 1, 2, 3, 4, as we go up, these energy levels are getting closer together. So the 4 to 3, this is a really small energy compared to the 2 to 1. So the 2 to 1 difference has to be much greater than the 4 to 3 difference of energy. So I'm going to get a longer wavelength photon for the 4 to 3 because that's our lower energy transition of these choices that result in emission. Number 6. The ionization energy of sodium is 496 kJs per mole. The photoelectric effect experiment is basically the idea we're going to shine a metal onto sodium and then see what photons of light cause an ejection of electrons. And it's going to take photons that have at least an energy of 496 kJs per mole. Let's think of what this ionization energy is for one sodium atom in terms of its ionization. Let's do that also in joules. So that we can use Planck's constant. We're going to need to use that in a minute. So let's convert the 496 kJs per mole and say, well, what's that ionization for a single atom? So that would just be the 496 kJs per mole. Now the ionization per atom would just account for 1 mole of sodium would be an Avogadro's number of sodium atoms. And then 1 kJ, so 1 kilojoule is, of course, 1,000 joules. So this, of course, will be a small number. 496 divided by 6.022 times 10 to the 23. and then times 1,000. I get 8.24 times 10 to the minus 19 joules. So I want my photon energy. I want the energy of my photon, which is equal to hc over lambda. We want the wavelength of this. I want this to be a greater energy or equal to the energy of 8.24 times 10 to the minus 19 joules. So I need the energy of my photon to be this energy per photon or greater. And so then if I apply my math, then my photon should have a wavelength that's less than or equal. So when I multiply the wavelength, the lambda, to the other side of the equation, the lambda is going to be less than or equal to hc divided by 8.24 times 10 to the minus 19 joules. And so I'm just going to do that math without writing it out, but 6.626 times 10 to the minus 34 times 2.998 times 10 to the 8 meters per second, divided by 8.24 times 10 to the minus 19. So I have joules times seconds for H, meters per second for the C, divide by joules. So I'm left behind just with the units of meters as not canceling. The only unit doesn't cancel. So my wavelength needs to be less than or equal to 2.41 times 10 to the minus 7 meters, and then multiplying that by 1e9 by 10 to the 9 is 241 nanometers. So we need that wavelength to be that wavelength or lower. And then sodium can lose an electron upon interaction with the light hitting the metal. So light of 241 nanometers or below has an energy of 496 kJs per mole or greater. So that gives us an energy per photon of 8.24 times 10 to the minus 19 joules or greater. And that's what we need, is a greater energy. That's lower wavelength. I'm going to skip 7. That's just a chapter 3/4 question that snuck its way onto this activity. Question 8, what type of orbital is occupied, or like this electron, sort of corresponds to this combination of N and L. So when N is 5, you may be confused into thinking that, well, L could range from these values here, but the key is that we're looking specifically at the combination of the 5 and the 3. Oops, I'm trying to write the orbital shape and the designation. Here would be S, P, D, F. Probably wouldn't expect you to know that 4 is actually G. No ground state element would use G orbitals, but this is going to correspond to a 5F orbital. So the N and L refer to a subshell. And so we have, a 5F orbital or a 5F subshell designation for this electron. And what's the most number of orbitals within a single atom that could share this combination of N and L? Well, it's all the ones that share that M sub L range of -3, -2, -1, 0, +1, +2, +3. So that's 1, 2, 3, 4, 5, 6, 7. So there should be 7 orbitals that have this 5F in this 5F subshell. 2 electrons each. 14 electrons could go into or could have that combination of N and L. So it's a 5F series with 7 orbitals. Doesn't ask about the electrons, but 2 electrons per orbital. Which atom below does not contain 7 valence electrons? Well, iodine, let's look at fluorine first. Fluorine is a 1s2, 2s2, 2p5. So clearly 7 valence electrons in the outermost shell. The outermost N value is 2. So we count both the 2s and the 2p, the outermost shell. Everything in a group together on the periodic table should share the same count. So iodine should also have 7 by the same reason. If you looked at its full configuration, it would be an iodine would follow krypton for a, let me look at, so it should follow krypton for a 5s2. Just make sure I get the right number for 5s2. And so we're filling into, what row are we filling into for iodine? We're filling in 1, 2, 3, 4, 5, the fifth row in the periodic table. So that'd be a 5s. And then we fill back into the 4, so it's 4d10. We haven't hit the F block. If you follow the elements, we don't go across an F block yet. F block doesn't come up till elements 58 through 70, or 57 through 70. And then we fill back into the 5p, so 5p, 5 across, and so our outermost shell is still, or in this case, is the n equals 5, and there's 7 valence electrons. Now, what about manganese? Manganese is an argon 4s2, 3d5 configuration, and so we end up with this 2, but we also add the 5 here because we're in a lower end subshell, but it's unfilled, so we're going to count the 2 and the 5 for plus 7. So I have 7 for all 3 here. Now nitrogen's the one that's out that doesn't have 7. It would be the answer to the question, because nitrogen's a 1s2, 2s2, 2p3, and only these 2 and the 3, so it only has 5 valence electrons, and it doesn't have 7. So the atom that does not contain 7 in this case would be nitrogen. A few more questions for this packet. How many total valence and core electrons does tin have? Element Sn. Tin is element number 50. So it's also going to follow like iodine. It's going to follow from the krypton configuration. So we can write its configuration as krypton. That's 36 electrons. And then krypton, 5s2, 4d10, 5p2, highest n is 5, so these are our highest n. So we have 4 valence electrons. This is filled, so we don't count that lower subshell because it's a filled subshell. And so we have 4 valence electrons, and then all the remaining electrons are what we call core electrons. So all the remaining 46 electrons are the core. The idea is the outermost valence electrons interact with each other in bonding. So identifying the valence electrons is useful when we start thinking about chemical bonding, which will be a topic we get into in the next couple chapters. Consider the ground state configurations of the expected for the atoms below. Which atom contains the most unpaired electrons? So, I mean, this problem is cluing us in that almost every case, if we ask you for a configuration, we're trying to get you to give the expected one. And not worry if these atoms might contain an anomaly. So just give us the ordinary configuration you expect. So titanium is a argon 4s2, 3d2, 2 across the D block. Vanadium is the same but a 3d3. Iron is the same but a 3d6, 6 across. Nickel is the same but a d8. And then the zinc atom is a d10. So let's start with zinc, actually. So zinc has all of its electrons spin paired in that D subshell, and all the lower core electrons, too, are spin paired. So we have 0 unpaired electrons for zinc. So the unpaired electron count total for zinc is 0. We have 1, 2, 3, 4, 5, 4, and then 2 unpaired for titanium. All 3 unpaired. So I'm just applying Hund's rule. 3 unpaired. For iron, I have to spin pair one set of the electrons to get 6 into the D block. And so I have 5d orbitals. I maximize the spin up to 5, and then the 6 I got to spin pair. So I have 4 unpaired for iron, and nickel is only going to have 2 that are net unpaired. So I'm looking for how many electrons are net unpaired. In the case of nickel, it's just these 2 here. And so nickel only has 2. So the most unpaired electrons, the atom with the most unpaired count here would be iron. Then last question of this activity, or this quiz, is which of the following sets of quantum numbers are possible for an electron in an atom? So this is just basically saying which of these quantum numbers are a legal or an allowed set of quantum numbers. If we look at the first set, 2, 0, 2, 0, and m sub l minus 1, and then plus a half, everything's good here except for the m sub l. The range of m sub l ranges from just minus l to 0 to plus l, all integers between. And if l is 0, the only possible m sub l is 0. And it's because this is referring to the 2s. So this is a 2s orbital. There's only one of those orbitals. Should be reflected by having only one possible m sub l value. So the m sub l is wrong, so that's not a valid set. 4 and 2 for L, that's fine. L can go up to n minus 1, so that's good. And then plus 2 is an allowed range for m sub L. Minus a half, the m sub S is either plus 1/2 or minus 1/2, and that's it. So 2 is allowed. 3 looks good. We have an n of 5, L of 3, m sub L can be 0, that's fine. The m sub S is negative a half, so that's perfectly reasonable. 2 and 2 for n and L is wrong because the most L can be is n minus 1. So 4 is out because of the L value is not an allowed L value. N and L, that looks good here. 3 and 1 are allowed. Minus 1 for m sub L, that's good. But now 0 is not allowed for the m sub S. And so the only valid configurations here are 2 and 3.